So now I can use in step 4, then I can find out for other two frequencies what are the MdB values. Now MdB value at omega C2 is slope at omega C1 log omega C2 by omega C1 plus MdB at omega C1. So when you substitute all the data here, you will be getting it as minus 16.5 because at omega C1 the slope is 0. So when it is 0, the same MdB value is coming here, that is minus 16.5. Then at omega h also we can find out what will be the magnitude value, that is going to be minus 28.5. So then the table, if you look at omega and MdB values, when it is 0.1 I have 17.5, when it is 5 it is minus 16.5, when it is 10 minus 16.5, then when it is 20, that is omega h, then it is going to be minus 28.5. So I have 4 points from this table. Those 4 points I can locate and I can draw the straight lines, which is the magnitude plot. Next, look at how to get the phase plot. So when you look at the transfer function, from the transfer function we can write the phase angle expression. We know that for any first order term or any finite term, then we can write, let us say if it is a plus jb, then we can write it as a tan inverse of b by a, which means imaginary part by real part. So if it is in denominator you will get minus, if that is in the numerator you will get plus. Then with that we can write the phase angle for the numerator 0.75, it is a constant, that will be 0, and I have 1 plus 0.2 omega, so that will be tan inverse of 0.2 omega, and denominator I have 1 j omega, therefore minus 90, and for quadratic factor we can write like minus because of the denominator tan inverse of, so I have imaginary part of the quadratic term is 0.16 omega upon 1 minus 0.01 omega square. So this is the phase angle expression. But this phase angle expression here, this is valid for certain range of frequencies. So when you prepare a table omega versus phase angle, then we need to look at this particular term and we should take care about it. So we can simply approximate this particular term as like this, one way of approximation. So what is the omega n? Omega n is omega C2, that is 10 radian per second. So before that we will use one formula, after that we will use another formula. So when omega is less than omega n, then I can use the formula as phi is equal to, so I have already have plus tan inverse 0. Omega and minus 90 as it is, and minus tan inverse of, I can take 0.16 omega because I have omega value less than omega n. So when omega is greater than omega n, then what I can do is the first two terms are as it is, tan inverse of 0.2 omega minus 90, then I will take plus here, then tan inverse 16 by omega, here it is 16 by omega. So when you do this, you will get approximate values of the phase angles for corresponding omega values. Otherwise, directly take the first expression and we will add 180 degrees to the whenever omega crosses the omega n value. So that means I can use this expression also, phi is equal to tan inverse of 0.2 omega already there, minus 90, minus this expression is also there, tan inverse minus 0.1 omega by 1 minus 0.01 omega square. So this is valid for omega is less than or equal to omega n. So when omega is greater than omega n, then the same expression, then I am going to add plus 180 degrees. So when you add plus 180 degrees, we can take care of that problem with the omega n. So with these values, when you tabulate, then initially we will look at when omega is 0, what will be the phase angle, that is going to be minus 90 because there is one pole at the origin. And similarly when omega is infinity, then what will be that? So we have 3 poles, that means 2 complex poles and 1 pole at origin, there is 1 0. So 3 minus 1 will be 2. So 2 into minus 90 is minus 180 degrees. So it changes from, that means your phase angle values will be from minus 90 to minus 180 degrees. Let us look at some of the specific values. We can take any number of omega values and corresponding. If you take more number of values, then your plot will be more accurate. So when it is 0.1, it is around 90 degrees. We have minus 90 degrees. Then let us take at omega is omega C2. at omega n, then you are getting it as minus 116. So similarly, when it is 200, we will be getting as minus 77. It is going to minus 180 degrees. So we can have all the table with us to plot the magnitude as well as the phase plots. So take the semi-log graph sheet. Then starting with we are always taking omega L value as a 0.1. Therefore, the leftmost side is 10 power 0, that is 0.1. Then again it is 10 power minus 1, that is 0.1, 10 power 0, 10 power 1, 10 power 2. So 0.1, 1, 10, 100 and so on, we can take the frequencies. Now the left side here I can have MdB values depending upon the range, and the right side I can have the phase angle values depending upon what are the phase angles which are there in the table. Now I just locate the points. We know at omega is 0.1, then we have already a 17.5 dB place, so I can locate here. Then we have 5, the 5 is it is going to be minus, so we have minus 16.5, then 10 is also minus 16.5, then 20 is minus 28.5. So I can locate all these points, then I can draw the magnitude plot, straight lines. Then the initial slope is, minus 20 dB for decade. This is 0 dB for decade. Again I have minus 40 dB for decade because of the quadratic factor at omega C2, which is the omega n. Now, so you can also plot the phase plot. So when you take the phase plot, so we have like this. So we are taking all the points, we are locating. So once you locate, you will be getting the phase plot, which is starting from minus 90, it is going up to minus 180 degrees. Now you closely observe the omega GC, omega PC. From that we can say whether the system is stable or not, stable or unstable or marginally stable. So first look at what is the omega GC value. So omega GC means where the magnitude plot intersects the 0 dB line. So in magnitude plot 0 dB line is a reference. In phase plot minus 180 degrees line is the reference. So when you look at closely here, it is crossing at this point. So when omega GC is omega is 0.8. So 0.8 is the omega GC. Then take that point, we can vertically draw the line onto the phase plot. Then we can find out what is the corresponding phase angle. That is going to be minus 88 degrees. So 5 GC is minus 88 degrees. Then phase margin is 180 plus 5 GC. That means 180 minus 88. It is going to be 92 degrees. The phase margin is plus 92 degrees from the omega GC. Similarly, you can look at the phase plot where it is crossing minus 180 degrees, and it is very clear that the phase plot is starting from minus 90 is going to minus 180 degrees. It is not at all crossing the minus 180 degrees. Therefore, omega PC you can take in as infinity, then corresponding gain margin is also infinity. Then from this plot, what is the summary? We have omega GC and omega PC. Omega GC is at 0.8 and corresponding 5 GC is minus 88 and phase margin is plus 92 degrees. And omega PC is infinity, gain margin is also infinity. Therefore, gain margin is infinity, phase margin is infinity. So my closed loop system is stable system.